All right, let's get right into it. Today we're going to tackle two really powerful concepts that can level up your regression models: bootstrapping and regularization. These are the kinds of tools that move you from just building a model that works to building one you can actually trust. Super important stuff if you want to know how much confidence to put in your results.
So you've put in the work, right? You've cleaned your data, you've built a linear regression, and boom, you get your coefficients. The model tells you that for every unit of x, y goes up by 0.9. Great. But here's the question that should keep you up at night. If you went out and got a slightly different set of data, would that number still be 0.9? Or could it be 5? Or maybe even -2? Just how stable is that number, really?
And that's where this amazing technique called the bootstrap method comes into play. The big idea here is actually pretty simple. It asks, what if we could just pretend to collect new data sets over and over again? Well, bootstrapping lets us do exactly that. It's a way of resampling from the data we already have to see how much our estimates would bounce around. It's a fantastic way to measure uncertainty without ever leaving your computer.
And here's how it works. It's actually a pretty straightforward process. First, you create what's called a bootstrap sample. Just picture your data set as a bag of marbles. You reach in, pull one out, record it, and here's the magic trick. You put it back in the bag. Then you do it again and again until you have a new sample that's the same size as your original. Now, because you're replacing the marbles, some might get picked a few times and some might not get picked at all. You then fit your model on this new, slightly weird sample and write down the coefficients. And then you just do that whole thing again, maybe 1,000 times.
So after you've done this 1,000 times, you don't just have one single value for your coefficient. Nope, you have 1,000 different values. And what this gives you is a beautiful distribution of all the possible values that coefficient could take. It's no longer just a single point. It's a whole landscape of possibilities, showing you the inherent uncertainty in your estimate.
So what's the payoff for all this work? Well, this distribution is incredibly useful. For one, we can just calculate its standard deviation, and that gives us the standard error of our coefficient. If that number is small, great, we can be pretty confident in our estimate. If it's big, that's a red flag that our coefficient is unstable. We can also use this distribution to calculate confidence intervals and even p-values to see if our variables are statistically significant at all. It's a massive upgrade for understanding our model.
Okay, so bootstrapping is all about understanding confidence. But let's switch gears to a totally different problem. What happens when your model is just too complex? It has dozens, maybe hundreds of variables. It might predict your training data perfectly, but the moment you show it some new data it's never seen before, it just completely bombs. What's going on there?
Yeah, this is a classic problem, and it's called overfitting. What's happening is that your model has gotten too clever for its own good. Instead of learning the true underlying pattern in the data, what we call the signal, it started memorizing all the random meaningless quirks. It's memorized the noise. It's like a student who crams for a test by memorizing the answers, but has no clue how to solve a new problem.
So how do we fight back against overfitting? One of the best weapons we have is a technique called regularization. It's a really smart idea. Basically, when we're training the model, we don't just tell it to minimize its errors. We also add a penalty for being too complex. This forces the model into a trade-off. It has to find a way to fit the data well without letting its own complexity get out of control.
So how does the model know it's being complex? Well, regularization measures complexity by looking at the size of the coefficients. See, a model with really large coefficients is often a sign that it's overfitting. It's putting way too much importance on just a few features. So, by adding a penalty based on how big those coefficients get, we gently nudge the model to use smaller, more stable values.
Okay, a penalty. I get the concept. But how does that work in practice? I mean, how do you actually calculate it? And is there just one way to do it, or are there different kinds of penalties you can use?
Great question. And that brings us to the two most popular types of regularization. First, you've got ridge regression. This one adds a penalty that's based on the sum of the squared values of the coefficients. It's really good at taking large, wobbly coefficients and shrinking them down towards zero. Then you have lasso regression. It penalizes the sum of the absolute values of the coefficients. Now, that sounds like a tiny difference, but the effect is huge, because lasso can take those coefficients and shrink them all the way to zero.
And this ability to just zero out coefficients is Lasso's absolute superpower. What it does is create sparse models. That's just a fancy way of saying models with fewer variables. If the feature isn't really helping, Lasso will just kick it out of the model by setting its coefficient to exactly zero. This is amazing because it's basically doing automatic feature selection for you, leaving you with a simpler, more robust, and often much easier to interpret model.
And this really gets to the heart of why we do this. I mean, think about this quote. At the end of the day, our goal is usually to explain something. And a simple model with just 3 important factors that you can actually understand is often way more useful than some monster model with hundreds of factors that gets a slightly better score but is a complete black box. Regularization helps us find that simpler, more useful story.
So there you have it. We've got bootstrapping to tell us how much to trust our numbers, and regularization to keep our models from getting too complicated. They're both about moving past a single right answer and instead embracing uncertainty and simplicity. It really all boils down to that classic trade-off, finding that perfect balance so your model is just right. So you have to ask yourself, in modeling, is less really more? The art is knowing when the answer is yes.
And that wraps up our look at bootstrapping and regularization. If this explainer helped you out, do us a favor and hit that like button, share it with someone, and subscribe for more deep dives into the concepts that matter. Thanks for tuning in.